Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to explain CFD heat transfer analysis, parametric study and optimization of a single pass shell tube heat exchanger using SolidWorks 2022. This is the model. Shell tube heat exchangers may be of different types. It may be single pass or it may be double pass. In this case we are considering the simplest one. It is single pass shell tube heat exchangers. For understanding the geometry, let us have a segmented view of this model. We can cut it from a specific plane. Let us cut it from front plane and drag it a little bit to see the specific view. This is the model. So from here we'll provide hot fluid. In this case we are planning to provide hot water from this one at a temperature of 100 degrees centigrade, and this hot air will be accumulated at this location and it will be passing through these small dirt tubes, and at the end of the tubes again hot water will be collected at this location and finally it will be coming out from this opening. At the same time we are having some cold opening. This is the cold opening. From here we will provide cold water at a temperature of 20 degrees centigrade, and there will not be direct mixing of hot and cold fluid, and the tubes are containing hot water at a temperature of 100 degrees centigrade, and surrounding these tubes we are having cold water that is for cooling purpose. So the tubes are carrying hot water and these tubes are surrounded with cold water. You can see at this location this is the exit of cold water and this is the exit of hot water. This is a very simple one. In this case we'll consider only simple CFD analysis. Next to that we'll go for some parametric study, and finally we'll go for optimization. So without wasting time, let us start our simulation. For starting the flow simulation environment, we need to start with wizard, and we are keeping the name of the project as project 2 because already we have done one. Next to that we need to select the unit system. We'll select the unit system as SI, and next to that from parameters we'll select temperature as degrees Celsius. Next to that, the type of analysis, this is an internal analysis, and from physical features we need to select fluid flow with conduction, and gravity will be involved because hot water has a tendency to go up and the direction of gravity is y as indicated by this arrow in the upward direction. So along y it will be minus 9.81 meter per second square, minus 9.81 meter per second square, and along z it will be 0. Next to that we need to select liquids, and in this case we are considering single fluid or single liquid as water, and we will consider water from two different subdomains at different temperatures. So we are considering fluid as water. Next to that, materials. In this case we are considering two different materials. The outer casing is made up of steel 321 and the tubes containing hot water is made up of copper. So at this moment we'll consider copper only. It will come from metals, and the other metal will be selected during application of boundary conditions. So at this moment we are selecting copper only. Next to that, default outer wall thermal conditions and roughness we are considering, and finally pressure will be 1G1325 Pascal and temperature will be 20 degrees centigrade, and solid parameters also it will be 20 degrees centigrade. Let us finish this. You can see this is the computational domain. Next to that we need to hide this domain, and we can apply different fluid subdomains because in this case we are considering water at different temperatures from two different locations. And for applying these fluid subdomains, let us have a segmented view of this model. We can cut it from front plane, go and check, and we need to apply different fluid subdomains. Let us rotate this one a little bit to select the specific locations of these fluid subdomains, right? So insert fluid subdomain and let us select this location. From here we'll provide hot water at a temperature of 100 degrees centigrade, and temperature we need to provide from here, it will be 100 degrees centigrade. Go and check, done. Another fluid subdomain is needed, that means cold fluid or cold water should be passing from this one, that will be having temperature of 20 degrees centigrade. So insert fluid subdomain, and it will be water at a temperature of 20 degrees centigrade. It will be passing from this one. So this is the fluid subdomain for cold water. You can see that the volume of cold water is much more than that of hot water, so will not have that much of temperature decrease at the end. So for that to have a much increase or decrease of temperature, we need to vary the mass flow rate of hot water, right? So green check. Two fluid subdomains are defined. Next to that, we need to select materials, insert solid materials, predefined alloys, and the outer casing is made up of stainless steel 321, and we can select the material from here. This is a shell. This is made up of stainless steel 321, green check, and we need to provide copper for the tubes. So solid materials, insert solid materials, and predefined metals, it will be made up of copper. We need to select copper materials from inside. These are the copper tubes. You can select it from here. You can select all the tubes. You can move it down to select the last one. First one is selected. Now shift, and we will select the last one. All the tubes are selected, and it is made up of copper. Green check. Both the materials are applied. Now we need to apply our boundary conditions, and for applying boundary conditions, it is suggested to have a segmented view of this model. So we'll cut it from a specific plane. Let us cut this model from front plane, and from both end we'll provide hot water and cold water at same velocity of 0.1 meter per second. So boundary conditions, insert boundary condition, and we'll provide inlet velocity of hot water from this opening. Inlet velocity will be 0.1 meter per second. And thermodynamic parameters, it will be 100 degrees centigrade. Green check. First boundary condition is applied. Next to that, we need to apply second boundary condition, that will be cold water from this location. So insert boundary condition, and it will be cold water from this location, and it will be again same velocity. It will be 0.1 meter per second. Green check. That means from both the hot and cold opening, we are providing water at the same velocity of 0.1 meter per second, right? Two boundary conditions are applied. Next to that, we need to apply another two boundary conditions, that is the atmospheric pressure at the exit locations. Insert boundary condition, it will be environmental pressure or atmospheric pressure at the exit locations. First of all, we'll select hot exit. Green check. It is done. Another boundary condition is needed, that is the exit of cold water. Boundary conditions, insert boundary condition, and it will be environmental pressure or atmospheric pressure at the exit of cold water. Selected. Green check. So all the boundary conditions are applied. Next to that, we need to find goals. We can have a lot of goals, but in this case our main aim will be to find out temperature at the exit locations of hot water and cold water. By the same time, we want to find out LMTD, that is the effectiveness of this heat exchanger. It is logarithmic mean temperature difference, LMTD. and that will be obtained by using equation goal. First of all, we need to find out two surface goals, that is the temperature at the exit surfaces of cold water and hot water. So goals, insert surface goals, and we're going to see average temperature of fluid at the hot and cold water exit locations. First one is the phase one, that is hot water exit, and second one is the cold water exit, and we want to create goals for each of the surface separately. Green check, and we can rename this one as average temperature of hot water at exit. Similarly, the second one, we can rename this one as average temperature of cold water at exit. Average temperature of cold water at exit. Done. Both the surface goals are defined. Next to that, we need to find some equation goal, that will be LMTD, that is the effectiveness of the heat exchanger. Goals, insert equation goal, and that equation goal can be obtained from the boundary conditions. Now the LMTD is equal to the difference in temperature of hot water and cold water minus difference in the temperature of hot water exit minus cold water exit divided by ln of difference of hot water and cold water divided by difference in temperature of the hot water exit and cold water exit, right? So we can obtain from here itself, or we can get it from these boundary conditions. So it will be obtained from boundary conditions, that is inlet velocity temperature, that is the inlet temperature of hot water. Before that, we need to provide some kind of bracket. We should initiate this one with a bracket, minus inlet velocity to temperature, that is the temperature of cold water at the entry location, bracket closed, minus, again bracket started. It will be obtained from the surface goals. We can generate the surface goals from here itself. Average temperature of hot water at exit minus average temperature of cold water at exit, bracket closed, divided by ln of. You can copy the previous things and paste it here inside the ln, and we can remove this minus sign by division sign. It is done. So we can rename this one as LMTD. It is actually the difference of hot water and cold water minus difference of hot water exit minus cold water exit divided by the ln of hot water minus cold water divided by difference of hot water exit minus cold water exit. This equation goal, we can rename this one as LMTD. Done. All the goals are defined. Now we can run this. We have already done this one, so we can directly see the results from project 1. Let us go back to project and see the results. We need to load the results. Results are loaded. For viewing the dynamics of flow particles and define pressure and temperature cut plots, we can make the model completely transparent. Let us make the model transparent. The model is completely transparent. Now we can see our results from different planes. First of all, we'll see cut plots of pressure and temperature from different planes. So insert cut plots, and we're going to see temperature distribution, temperature of fluid from front plane. Exterior pressure, we're going to see temperature of fluid from front plane. Crane check. Now it is better to see this one in the form of an animation, and we'll view this one from front plane. Let us have an animation of this one. It is clearly seen that from this opening we are providing hot water at a temperature of 100 degrees centigrade, and from this opening we are providing cold water at a temperature of 20 degrees centigrade, and these are the exits of hot water and cold water. And both the exit of hot water and cold water, we cannot see that much of change in temperature. Very little change in temperature is there, because at the beginning itself I told that the volume of cold water is so high compared to volume of hot water. To change the temperature of hot water exit and cold water exit, we need to provide hot water at a higher rate or with a high velocity. In parametric study, we'll see that one, right? Now we can see this one from different planes also. We'll see it from right plane. So let us clear and hide it. And we want to see this one from right plane. Edit definition, and we want to see from right plane. Run check, and we can orient this one to right plane. Let us see this one in the form of an animation. Cut part 1, let us play. You can see how hot water and cold water is passing from different locations. Let us rotate this one a little bit. We are having 4 wafers inside this single pass shell tube heat exchanger. These wafers are provided at alternate locations. Next to that, we need to see pressure distribution. So clear and hide, and insert cut plots, and that one will be pressure distribution. Instead of temperature of fluid, we want to see pressure. Grid check, that is from front plane. Let us play this. This is pressure distribution through the single pass shell tube heat exchanger. You can see pressure at the down level is high, and at the top level it is less. And we can view this one from different planes also. Let us clear and hide. And we want to view the same from right plane. Cut plot 2, edit definition, and we want to see this from right plane. Grain check, and we can orient this one according to right plane. Let us see the distribution in the form of an animation. Cut plot 2, play. This is pressure distribution through the single pass shell tube heat exchanger. Let us clear and hide this one, and next to that we need to see surface plots. Clear and hide, and we see surface plots. We see temperature distribution through the surface plots. Insert surface plots, and we have to see all surfaces, and you have to see temperature distribution through all the faces, and it will be temperature distribution, temperature of fluid at the boundaries. Green check. It's clearly seen that temperature at the entry of hot water, it is red, that is its temperature 100 degrees centigrade, and this is the entry of cold water, its temperature is 20 degrees centigrade. In between, at the shell boundary, temperature is very less. It is in the range of 20 to 29 degrees centigrade. And again, at the exit of hot water, its temperature is little higher. It is in the range of 29 to 37 degrees centigrade approximately, as seen by this blue color. And here in this case, we can see some mixed zone is there with different ranges of temperature. I have already told before, because of much higher volume of cold water, the temperature at the exit of hot and cold water, we could not see that much of gain or that much of decrease. Now this temperature can be varied by increasing the mass flow rate of hot water or velocity of hot water. That one we'll see from parametric study. Okay, so let us clear and hide this one. Next to that, we'll see dynamics of flow particles. That means how different flow particles will be moving from one point to another point, right? That is very important part. So flow trajectories, insert flow trajectories, and instead of 20 numbers, we want to see 200 numbers of flow particles will be moving through this shell tube heat exchanger. Let us select this one. Select other. It is lead number 1. Again, we need to select this one. That is the entry of hot water. Select other. This is lead number 4. And again, you need to select the exit locations also. Select other. It is lead number 2. And finally, the exit of hot water. Select other. It is lead number 3. Selected. Green check. Now particle study is being generated. It will take some time to complete the particle study. It is done. Now let us see the dynamics of flow particles, right? Let us view this one in the form of an animation. Flow trajectories. Let us play. We can orient this one from front end. You can see we can increase the size of these particles, and that will be better for viewing. Let us clear and hide this one, and we'll increase the size of this one. Clear and hide. Next to that, flow trajectories, edit definition, and we want to increase the size of this one. This is 200 numbers, and the arrow size, instead of 0.01 meter, we'll make this one as 0.05 meter. Go and check. It is better to see in this form. Let us play this. This is the dynamics of flow particles. You can see from this one, red particles, that means temperature of this hot water at this location is 100 degrees centigrade, and at this location some kind of circulation is occurring, and from here we are providing cold water at a temperature 20 degrees centigrade that will be surrounding these tubes. And finally, at the exit location, you can see this is the exit of hot water and this is the exit of cold water. And in this case, you could see that temperature at the exit of hot and cold water is not that much of varied. To vary the temperature of exit locations, you need to provide hot water at a higher velocity. That one will be done during parametric study. Okay. You can see here some kind of vortex motion is created at this location. That is not wanted. Let us clear and hide this one. Next to that, we need to see our goal plots, and we select all the goals and we will see the results from Excel. So let us export to Excel. First one is average temperature of water at the cold exit. Initially temperature of cold water was 20 degrees centigrade, and here you can see that after 370 numbers of iterations, at the exit of cold water the temperature is 21.638 degrees centigrade. That means there is a very little increase of temperature at the cold water exit, right? Next one, you see average temperature of hot water at the exit location. Initially average temperature of cold water exit was 20 degrees centigrade, and finally after 370 numbers of iterations, its temperature at the exit location is 31.90 degrees centigrade. So we cannot see that much of change in temperature at the exit locations. And let us see the LMTD value. LMTD value we got 80. Let us close it. We could not see that much of change in temperature at the exit locations, and that one we'll see during parametric study, right? Next to that, we'll go for some kind of parametric study. This parametric study we have already done. Let us see the parametric studies, that is design of experiments and optimization. In this parametric study, we have selected the velocity of hot water in the range of 1001 meter per second to 10 meter per second. That means in this parametric study, we have selected a wide range of velocity for the hot water. We have started the velocity of hot water as 0.001 meter per second, and we have finished with a velocity of 10 meter per second. Let us see the results from here. Goals. We can see that when the velocity of hot water at the entry location was 0.001 meter per second, in that case you can see that average temperature at hot water exit is 20.13 degrees centigrade, and that of cold water exit is 20.02 degrees centigrade, and LMTD is 79.77. In all cases you can find that LMTD is 79.77. The second experiment, when the velocity of hot water at the entry location was 0.01 meter per second, in that case you can see average temperature at hot water exit is 21.23 degrees centigrade, and that of cold water exit is 20.16 degrees centigrade. In experiment number 3, when the velocity of hot water inlet is 1 meter per second, in that case you can see that huge amount of change in temperature at the exit locations. The average temperature at hot water exit is 87.57 degrees centigrade, and that of cold water exit is 41.55 degrees centigrade. In the experiment number 4, when the inlet velocity of hot water is 5 meter per second, then you can see that average temperature at the hot water exit is 96.66 degrees centigrade, and that of cold water exit is 74.31 degrees centigrade. And finally, in experiment number 5, when the inlet velocity of hot water is 10 meter per second, in that case you can see that average temperature at hot water exit is 98.20 degrees centigrade, and that of cold water at exit is 84.65 degrees centigrade. It is clearly seen that when the inlet velocity of hot water is increasing, in that case we can see huge amount of increase in temperature at the exit locations. Both at the exit of cold water and hot water we can see remarkable change in temperature, right? Now from this analysis you can see that if you want to have a specific temperature at the exit location, we can have some idea from this parametric study. Suppose we want to have the temperature at the exit of cold water to be 50 degrees centigrade. In that case our range should be from 1 meter per second to 5 meter per second. You can see it clearly. If we want to achieve a temperature of 50 degrees centigrade at the exit of cold water, in that case our velocity of hot water should be in the range of 1 meter per second to 5 meter per second, right? Now let's start that optimization. This optimization we have already done. Let us see the optimization results from here. You can see that we have selected a range of 1 meter per second to 4 meter per second, and we want to achieve a temperature of 50 degrees centigrade at the exit of cold water, right? So let us see the goals. You can see it has undergone 18 numbers of calculations. Optimization done. You can see the results from here itself, right? So Initially it has started with a maximum velocity of 4 meter per second, and next case it has started the iteration with 1 meter per second. In this way it has tried to minimize the gap and try to optimize the case, and with 18 numbers of iterations we could optimize our results. You can see at the design point number 18, when the velocity of hot water at the inlet location is 1.4018 meter per second, in that case the temperature at the exit of cold water is 50.009 degrees centigrade. That means we could achieve our target, right? And that target was achieved with a discrepancy of 0.000978. It is very less, so it is good result. Like this way we can optimize any of the results as per our requirement, right? So with this one we'll conclude our today's analysis. It is a very simple analysis of a single pass shell tube heat exchanger. In this case we have done one CFD analysis, parametric study and optimization, right? Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.